Today's lesson is on properties of exponential functions, where we're looking at how to graph an exponential function. I sort of showed some exponential functions yesterday, but I didn't talk too much about how they are graphed or how to create them. So the parent function of an exponential, right? If you think back to your parent functions, you remember there was x squared, absolute value of x, square root x, and so on. The parent function for an exponential is y, or f of x, let's say, is equal to b to the power of x with two conditions, okay? b is not allowed to be 0, not allowed to be 1, and b has to be greater than 0. Okay, so this is an exponential function, the parent. So one of the things that makes exponential functions a little bit different from a regular function is that there are many different parents. There's 2 to the x, there's 3 to the x, there's 7 to the x. So like whatever the b value is, that is part of the parent function. So it's not like x squared where every single parabola comes back to the same parent. In exponential functions, every base, that's why it's b, every base has its own parent. So like 7 to the x is a different parent function than 2 to the x and 3 to the x and so on. Like all of these are different parents. Now, that being said, they're all exponential functions and they all have certain things in common. Let's go through a quick explanation of why it's the case that b cannot be 1 and b must be a positive number. So what I'm going to do here is I'm going to graph what I just said, b to the power of x. It's going to ask me to make a slider so it knows what I mean by b. And I do so. And exponential functions, you can see, have, they kind of like, on one side, they have extremely rapid growth that we've talked about in this unit already. And on one side, they have extremely rapid decay down to 0. So it never actually gets to 0, actually. If you stretch, you could always stretch this up higher and see that the function never actually reaches 0. Like it gets really, really close, obviously, but I could keep doing this. I could keep stretching it over and over again, and we would find that it never reaches 0. Now, another interesting thing about exponential functions is the point 0, 1. The point 0, 1 is on all of them. Right? Every exponential function passes through the point 0, 1. So that's helpful. Right? No matter what our base is, we always have a point that we can start with, and that point is 0, 1. Now, let's look at the difference between when b is above 1. So for example, here's b is 2. You can see this is exponential growth because from left to right it's rising. When b is 3, it's just faster growth. When b is 4, it's even faster growth. When b is 5, it's really fast growth, and so on. So the bigger b is, the faster the function's going to grow. Now what about when b is a fraction? When b is a fraction, you actually switch, you reflect the graph to the other side, okay, and you now are looking at exponential decay. So it's not growing, it's decreasing at this point, right? So, from left to right, the function is going down. Now, as you make b closer to 0, if I make b closer to 0, the decay gets more rapid, okay? So this decay is extremely rapid, right? Like it brings the function all the way down very close to 0 within 2, right? Whereas the one I was looking at originally, the 0.75, it takes a while before it sort of approaches 0, right? Closer to 20. So we have this general phenomenon about what's going on in this function. Let's just write a couple of these notes down. When b is bigger than 1, you have growth. The bigger b is, the faster the growth. Okay, so that was the first thing we looked at. When we're looking at a base that's bigger than 1, you have exponential growth. When b is 0 is less than b is less than 1, so you have a number between 0 and 1, you have decay. The closer to 0, the faster the decay. Okay, so that would be one thing we've looked at so far. Now, what happens when b is actually 1? Because if you go back to what I said here, I said b is not allowed to be 1. So why not? Right? It's a really good communication question. I always ask this question, which is simply explain these restrictions. Right? So let's just type that under here. Communication. Explain the restrictions on b. Okay? So let's explain why b cannot be 1. So let's make b 1, and you know, we'll look at this and see. So if you notice that the closer I get to 1, the flatter the function gets. And if we just change this so that it can count up a little more precisely. Okay, so let's change it so it can. So you can see I'm just sort of raising it really, really slightly. And like you can see, the closer I make b to 1, the flatter the graph gets. Now at 1 itself, you actually have a flat line. And since a flat line is not an exponential function, i.e. it does not display exponential growth nor exponential decay, rather it is a linear function, right, that is just flat, we say when b equals 1, it's not really an exponential function. So the exponential function is you know, it's only really considered an exponential if b is either bigger than 1 or in between 0 and 1. So if b equals 1, then the function becomes linear and is no longer an exponential function. Why does it become linear? Well, we know that 1 to the power of 1 is 1, 1 to the power of 2 is 1, 1 to the power of 3 is 1. In fact, 1 to the power of anything, right, is always 1. So that's why when you do 1 to the power of x, you just get this flat line, and that doesn't exist. Well, it's not that it doesn't exist. It's just not exponential. Now, the other thing that happens is, what if b is 0? If b is 0, just drop it down to 0 here. So this is why b cannot be 0. If b is 0, you just get, again, you get a flat line, and you also get a flat line that has nothing in the negative region. And I might leave that open to you. I'm going to post that question to the website, actually. Why don't we just go do that right now? We'll just go down here to the activity feed. Why is 0 restricted from the exponential function? Sorry, let's say why is b equals 0 restricted from the exponential function f of x equals b to the x. So